Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, we're going to talk about the deepest secrets of the entire universe. We're going to talk about gravity waves. We're going to talk about black holes. We're going to talk about big bangs and parallel universes, the cutting edge of modern physics. With us today is Dr. Jana Levin, author of a new book. It's called Black Hole Blues and Other Songs from Outer Space. She's a professor of physics and astronomy at Barnard College at Columbia University. Her previous books include How the Universe Got Its Spots and A Madman Dreams of Turing Machines. Now, gravity waves were discovered a few months ago, and it created a sensation in the media. People were saying that after 100 years after the prediction of 1916, the work of Albert Einstein, the last missing piece of relativity, has finally come into play with experiment. Scientists have detected colliding black holes in outer space, which themselves were predicted by Einstein, and we've detected the radiation from them with gravity wave detectors. Some people call this as an analogy like throwing a pebble in a pond. When you throw a pebble in a pond, ripples form, so the surface of the pond is not empty at all. The surface of the pond is dynamic, and it can sustain ripples. Well, that surface of the pond is space itself. The rock heating the surface of the pond is colliding black holes, the radiation emitted from colliding black holes, the most cosmic disruption of space and time since the Big Bang itself. And we've now measured it. A prediction made in 1916 was finally found in 2016. And with us today to discuss this is Dr. Jana Levin of Columbia University. And we should also mention that first we'll detect colliding black holes in outer space, but then we'll detect the Big Bang itself. Imagine baby pictures of the instant of creation, and maybe we'll detect an umbilical cord connecting our infant universe with a parent universe.
You're listening to Science Fantastic. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're going to talk about some of the deepest secrets of the universe, the deepest secrets of space-time as revealed by gravity waves, which were discovered just a few months ago, generating worldwide headlines. And most people's reaction was, huh? I mean, what is that? What the hell is a gravity wave? And why is it generating so much excitement in the scientific literature, hitting the headlines around the world just a few months ago? Well, with us today to talk about gravity waves is Jana Levin. She's a professor of physics and astronomy at Barnard College at Columbia. And she's also the director of sciences at Pioneer Works, which is a center for arts and sciences in Brooklyn. And she's also the author of a previous book, How the Universe Got Its Spots, and believe it or not, she is a novelist. How many theoretical physicists do you know are novelists? The book is called A Madman Dreams of Turing Machines. And today we're going to talk about her latest book, Black Hole Blues and Other Songs from Outer Space. So, Dr. Levin, glad you could be on Science Fantastic.
Thanks so much for having me.
Okay, well, the first question that we always ask our guests is, how did you as a youth get interested in science when we have so many distractions as a youth?
You know, I don't think I was a kid who thought I was interested in science. I remember the first time that I was in a dark enough place, having grown up in the city, on a summer trip to look up at the sky and really see the Milky Way and being incredibly affected by it. And I loved talking about the stars and thinking, but I actually didn't recognize it as being scientifically disposed. I don't think I acknowledged that I had a scientific leaning until college. So when I started college, I wanted to study philosophy and art, and it was kind of a revelation that my real interest was in mathematics and in physics.
And what was that? I mean, what steered you in that direction of going into mathematical physics?
You know, I was listening to a lot of philosophers argue about what Kant might have meant hundreds of years ago, and it was driving me crazy. And I just thought there's something wrong with the fact that we're still trying to decipher what somebody was trying to tell us. And I went to a lecture about Einstein and quantum mechanics and relativity, and it might be hard to understand for sure, but once Einstein taught us E equals mc squared, it belonged to everybody. It was something we all had forever. It was not something that 100 years later we're still arguing, what did he mean? And I just thought there's something about that transcends everything, and it just seems so powerful. And I just became very interested in it as a tool to understand the world.
Yeah, in fact, when I was a freshman in college, I went to Harvard, I took a course in philosophy. And what was so frustrating was nothing is decidable in philosophy. You can have your opinion and somebody else has another opinion, but so what? And you can write as many PhD theses as you want concerning what did he really mean anyway.
Yeah,
well,
and, math is the same for us on the other side of the galaxy. There's something about that that's really beautiful, and it's the same for somebody on the other side of the globe.
Yeah, I find that thought very reassuring, that if I write down an equation, that someone on the other end of the galaxy may be writing down that very same equation in different notation, and these are universal concepts. I mean, the question of universality and immutability is quite different from the world of English literary criticism and philosophy, don't you think?
Yeah, and I think that it's unifying. If we all stopped and acknowledged that people speaking different languages in different eras with different cultures all have this one sort of intellectual theme in common that they can share, that's true for all of us. I think there's something that's very promising about that.
And also, don't you realize that as we get into decidable questions in physics, that physics gets simpler every year, that English literary criticism gets more complicated as we debate what did Hemingway really mean by that sentence, while in physics we can summarize everything in terms of just a handful of equations, like Einstein's equations, the quantum theory. A handful of equations can summarize everything known about science. Isn't that incredible?
It is incredible. I mean, I think as a writer, I can get very interested in writing styles and different evolutions in writing, but as a physicist, it's the last place with a straight face that we can talk about beauty as being a valid interpretive tool, and that we can actually discover things by imposing symmetry and beauty and elegance as a rule. We can make actual physical discoveries that way. It's quite spectacular, really.
Yeah, it's hard to convey that feeling. When I was in high school years and years ago, I cried. I cried when I first saw what is called the Dirac equation. After struggling for many months with an earlier equation called the Schrödinger equation, then seeing the Dirac equation, I just broke down and cried. I didn't realize that nature could be so simple, beautiful, and elegant. Well, so much for propaganda.
Okay.
Let's get into the substance of your book.
For all of us.
Right. The book is called Black Hole Blues and Other Songs from Outer Space. So let's talk about your book. First of all, it was in 1916 that Albert Einstein talked about predicting gravity waves, but he didn't think that in his lifetime there would be instruments capable of detecting gravity waves. So first of all, tell us, what did Einstein do in 1916?
Well, so as soon as he finally mathematized his general theory, his theory that gravity was really a theory of curved space-time, the first thing he thought was most important was to turn to gravitational waves. So the idea is simple. If something like the Earth curves space and time around it, then if the Earth moves, those curves have to move and adjust to follow the Earth. There would be ripples, he realized, variations in the shape of space and time itself, waves in the shape of space and time, so that if a gravitational wave were to pass us, we would be squeezed and stretched slightly. We would sort of bob on the wave like something floating on the ocean. And to generate the gravitational waves, you really need a tremendous amount of mass and energy concentrated and moving and dynamic. And he just, first of all, didn't believe there would ever be anything massive enough or cataclysmic enough to generate gravitational waves, these ripples in space-time, in any significant way. And also, he kept changing his mind about whether they were even real. So, in 1916, he said they were real, then later he said they weren't. By the 1930s, he was still changing his mind.
I see.
It's a hard problem.
Now, here's a question that even children ask, and that is, if the sun were to disappear right now the sun were to disappear, how long would it take for the Earth to feel it? Now, if you are Isaac Newton, nowhere in your equations is there a concept of time and velocity of gravity, so the Earth would instantly be spun out of orbit. But if you're Albert Einstein, how would you answer the question, if the Earth were to disappear, the sun were to disappear right now, what would happen to the Earth?
So Einstein, adhering to the limit of light speed, using that incredibly severe constraint to understand physics or to make his revelations, he would say that, first of all, the light from the sun would continue to come to us for 8 minutes. It's about 8 minutes before we realized it had gone dark, and then that would be catastrophic. And at the same time, waves in the shape of space-time would travel to us. It would take 8 minutes for them to get to us to communicate the fact that the sun was gone. So we would no longer be on this curved orbit, this circle around the sun. Suddenly, we would just kind of fly off in a straight direction. But it would take 8 minutes before it happened.
So even kids know that you can't go faster than the speed of light. Every fan of Star Trek knows that. And however, if the sun were to disappear right now, what you're saying is that even gravity cannot go faster than the speed of light. Is that what you're saying?
Absolutely. These waves in the shape of space-time would propagate towards us, telling us that the space was smoothing out, that the circular curve we're falling along around the sun would be gone. But this wave would have to take a light travel time, even though it's not light, and it's really important to emphasize that these waves and the curves of space-time are not a form of light. They're pure gravitational. They would travel at the same speed as light. And so it would take the same time for us to find out the sun had gone dark and that we were suddenly traveling in a straight line.
Okay. And also, even though a direct measurement of gravity waves would be extremely difficult, as Einstein himself realized in 1916, there was a Nobel Prize given to two physicists over a decade ago, looking at two pulsars that were chasing each other like a dog chases its tail, going in a death spiral. And if there really were gravity waves, it would seep energy into outer space, and so they would be in a death spiral. So explain that. Explain how is it that an indirect measurement of gravity waves could be done, even though a direct measurement, as you point out in your book, would be much more difficult.
Yeah, so this is in the 70s that the work was done, and it was in the 90s, I believe, when the Nobel Prize was awarded to Hulse and Taylor for their discovery of a new kind of pulsar. So what they looked at was a neutron star, which is a dead star that's not quite massive enough to become a black hole. It just becomes an incredibly dense, basically nuclear particle. A neutron, like a big giant neutron, and it's in their case it was spinning and emitting light like a lighthouse. It was a pulsar, which is just a kind of a lighthouse effect when these neutron stars spin, and they saw it orbiting a companion. And what they deduced, this is actually not Hulse and Taylor. It's interesting. I heard from Joseph Taylor, the Nobel Prize winner recently, who said that after the work they did for the discovery of the new kind of pulsar, which is the work for which they were awarded the Nobel Prize, they later looked more closely at the orbit and realized that neutron star was slowly spiraling into its companion. And the reason it was spiraling in is because it was losing energy to the creation of gravitational waves. I liken these to like mallets on a drum, where the drum is space-time itself. And these mallets are moving, and the slower they move, the weaker the waves they create in the drum. But they create waves nonetheless, and they lose energy and spiral in. Now, that pulsar will take 300 million years to spiral together. So we're not going to build a machine to look for the gravitational waves from that directly. They're too weak right now. But what they could do is by calculating the in-spiral time and matching it to the calculation, theoretically, of the energy loss to the gravitational waves, they could match that and realize it was a perfect match, and so indirectly deduce that gravitational waves were being created.
I've heard an analogy being made with molasses that if you store a spoon in molasses, you create, well, a wave that carries energy off. And as the waves move, you lose energy, and therefore, with two pulsars, you're in a death spiral. Well, let's move on to your book. Let's now talk about direct measurements of gravity waves, not indirect measurements. Let's talk about LIGO. What is LIGO, and explain how big these two machines are.
So LIGO was an idea that started just as kind of a thought experiment, really. Ray Weiss talks about this when he first started thinking about LIGO 5 decades ago. He was just trying to understand Einstein's prediction for gravitational waves, and he was having so much trouble. He said it was so hard to comprehend that all he could imagine was, how would I measure this? And he imagined that he could hang mirrors so that they were free to float in space-time. And if a gravitational wave passed, those mirrors would kind of bob on the wave like something floating in the ocean. And if he could keep track of the location of the mirrors, he could measure the ringing drum, record the ringing drum of space-time, and maybe even play it back as sound. Plug this recording, kind of like how an electric guitar works, where you pluck the string, it doesn't make a sound until the body of the electric guitar translates it through an amplifier. And it started as just what he called a haiku. And he built a tiny machine, a meter and a half long, to try to see if this was even something that could be done in the lab. The real machines, 50 years later, are 4 kilometers long. They're each shaped like an L, where mirrors are suspended at the ends of the L. And there's 2 of them, one in Louisiana and one in Washington State. And 50 years on, it's integrated to about $1 billion, and now is a team of about 1,000.
Okay, so it's a gigantic machine where we have 2 laser beams, like you pointed out, in the shape of an L. And I guess where the 2 laser beams meet, that's where you can pick up what are called interference patterns, right? The ripples of interacting black holes in space. So what did LIGO find? I understand they found evidence of colliding black holes in outer space. Could you elaborate? So I could just say that you'd only really need one arm. You wouldn't need the whole L. If we had very precise clocks, you could just keep track of the light travel time down one arm, and if the light took a little longer or a little shorter time, you would know if a gravitational wave had squeezed or stretched space along that arm. But there aren't precise enough clocks. So they build an L, they take the laser, they split it down the 2 arms of the L, and when the light comes back, if it interferes perfectly, then the light traveled the same distance along the 2 arms. If it interferes imperfectly, you can measure by how much the arms were squeezed and stretched. So it's really an ingenious way to get around the fact that we don't have precise enough clocks. So what happened in the actual detection that was made was 1.3 billion years ago, plus or minus a couple 100 million years, 2 black holes collided. Each one was about 30 times the mass of the sun. And instead of the pulsars that we talked about earlier, these 2 black holes were in the final throes of what was probably a very long life. Dr. Levin, we have to take a short commercial break. But after the break, we're going to enter the world of black holes and what happens when black holes collide, releasing a burst of radiation which we can now detect on the planet Earth with gravity wave detectors. And so let's take a short commercial break. And after the break, we're going to talk about colliding black holes in outer space.
You're listening to Science Fantastic. Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about some of the deepest mysteries of space and time. It was 100 years ago that an obscure physicist called Albert Einstein made a prediction concerning the nature of space and time itself, and the fact there should be ripples, like ripples on a pond. Think of throwing a stone in a pond and the ripples emerge from the center. These ripples would be ripples of gravity waves, which in principle could open up a new realm of telescopes. Instead of relying upon light, Instead of relying on radio, why not rely on gravity waves? Well, with us today to talk about these things is Dr. Jana Levin. She's a professor of physics and astronomy at Barnard College, and she's the author of previous books, including How the Universe Got Its Spots, as well as a novel. How many professors of physics do you know that are novelists? The novel is called A Madman Dreams of Turing Machines, and today we're talking about her latest book, Black Hole Blues and Other Songs from Outer Space. Well, where we last left off, we were talking about colliding black holes in outer space. First of all, give us a short explanation of what a black hole is and what happens if they collide.
So black holes were first proposed just as a kind of mathematical oddity. And Einstein knew very early on about the idea of black holes, although they weren't called that then. Karl Schwarzschild was a German infantry soldier who was calculating ballistic trajectories in the trenches on the Russian front in 1916 when he was reading Einstein's paper. And he came up with this solution where he just imagined, what if I took the mass of the sun and I concentrated all of it to a point? What would the curved space-time look like around that object? And he realized at some point space and time would be so strongly curved that to launch off this object, you would need to travel faster than the speed of light. And that wouldn't be possible. So the object would go dark because not even light could escape. And he sent this to Einstein. Einstein was very impressed with this mathematical model, and he helped it get published, but he didn't believe nature could possibly think of a way to form such a thing. If you imagine trying to crush a cup, it's very hard to do, to make it very small. I can't mechanically crush a cup and turn it into a black hole. It's actually incredibly hard to do. And so for decades, people didn't think that these would actually form in nature. It was many years before people realized, actually, if a star is heavy enough that when it runs out of nuclear fuel, it will no longer be able to resist complete gravitational collapse. And it will collapse under its own weight, forming a shadow around it, which is the event horizon, the region beyond which not even light can escape, and then it will continue to fall, the material that makes the star. And we don't know what happens to it in the center. But if you were to cross that horizon, that shadow of a black hole that formed from the death state of a star, there would be nothing there. There would be nothing there as you fell across. So black holes are really pure space-time curves.
Now, I understand that J. Robert Oppenheimer, the father of the atomic bomb, was the man with his student who came up with the idea of collapsing a star symmetrically, an implosion method, and he actually used that apparently for the atomic bomb. When he was designing the Hiroshima and the Nagasaki bomb, he realized the Nagasaki bomb could go through critical mass if you implode it. Except instead of using gravity, you would use, of course, chemical explosives to contract the plutonium. But apparently he was his work on the black hole that led to the Nagasaki bomb.
Yeah,
Okay,
I'm glad you bring that up, because it's not often known that in some ways that's Oppenheimer's most important contribution to physics, was his work on understanding that the nuclear processes in the center of a star were very similar to the nuclear processes in a bomb, and that they were not strong enough, those nuclear forces, to resist gravitational collapse, and that black holes would in fact form as astrophysical objects. It was kind of whimsical for him to work on that, but it was his most important contribution, and many people denied that it was right. This was in the 30s that he did that, but it wasn't until the 60s that people started to accept the work, and the name black hole was coined.
Okay, now let's talk about what happens when two black holes collide. What happens? Do they fly? Oh, we have to take a short commercial break. But after the break, let's talk about the collisions of massive black holes in outer space.
You're listening to Science Fantastic with Professor Michio Kaku. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about some of the deepest secrets in the universe. We're talking about black holes, we're talking about gravity wave detectors, and we're talking about a book called Black Hole Blues and Other Songs from Outer Space by Professor of Physics and Astronomy at Barnard College, Dr. Jana Levin. And also, if you go to my website, check out my Facebook site. We're up to, well, very close to 3 million. We're almost up to 3 million fans on Facebook. On Twitter, we're up to, let's see, over 300,000 people follow me on Twitter. Where we last left off, we were talking about black holes in outer space, which back when I was a grad student years ago, we were told that black holes are basically like unicorns, science fiction, fantasy, and we see them in outer space, and also we can now detect their collision. So tell us a little bit now about what happens when two black holes collide and how we were able to detect that with LIGO.
So black holes are, by definition, dark. They emit no light, they reflect no light, and the only reason we've ever postulated that black holes exist in the universe is because we see them tearing debris down around them. So indirectly, we're really looking at the effect that black holes have on other stars or other objects, other material. And in this case, it was the first time we were able to detect bare black holes with no debris around them as far as we can tell. And you could not see this with a telescope. So the two black holes are in their final orbits together. They're ringing space-time like mallets on a drum. They're emitting tremendous amounts of energy when they do so, and they're spiraling together, but it happens in complete darkness. And in the final fifth of a second, we recorded the gravitational waves emitted as the black holes collided and wobbled down to one final black hole that was about 60 times the mass of the sun, and then went quiet.
So in other words, we're witnessing some of the most violent events in the history of the universe.
Yes, it was the most energetic event we've ever detected next to the Big Bang itself. The power that came out in darkness, in the gravitational waves, exceeds all the power coming out in all the stars combined in our observable universe.
Absolutely amazing.
Amazing amount of energy.
Right, and so I'm pretty sure that the people behind this will probably win the Nobel Prize in Physics for just opening up this whole new category of science called gravity waves. And personally, I thought that if we did not discover gravity waves with LIGO, that would probably shake the whole foundations of modern physics, right? I mean, a huge chunk of modern physics would have to be thrown out the window if we did not discover gravity waves. What are your thoughts?
It's a good point that the gravitational waves themselves were not a surprise. It was just the difficulty in recording them. And if you think about what LIGO does, it really does act like a musical instrument to an extent where it's recording something. So as the wave traveled 1.3 billion years, it came from the southern sky. It hit the first observatory in Louisiana, where it was recorded. And there was somebody in the control room who could have heard it come through a speaker system and literally played back as what's called the chirp. You literally can hear the ringing drum. It's like taking a ringing drum, recording the shape of the drum, and playing it back as sound. 7 milliseconds later, it scoots across the continent and hits the machine in Washington, and it's recorded again. The thing is that it happens so quickly that the human ear can't actually parse it. But if you listen to the recording and it's slowed down so that we can hear it, it actually happens in the human auditory range. And what you hear is this scoop up in frequency as the black holes traveling near the speed of light orbit each other and finally collide.
Okay, well, let's take another short commercial break. And after the break, we're going to continue a discussion of black holes and the creation of the universe and gravity wave detectors.
You're listening to Science Fantastic with Professor Michio Kaku. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. on Science Fantastic. We're talking about some of the deepest secrets of Albert Einstein's theory of gravity. We're talking about the Big Bang. We're talking about black holes and what happens when they collide. We're talking about gravity wave detectors. And our special guest today is Dr. Jana Levin. The book is called Black Hole Blues and Other Songs from Outer Space. She's a professor of physics and astronomy at Barnard College of Columbia University. A previous book was called How the Universe Got Its Spots, and she's also a novelist. How many physicists do you know write novels? The novel is called A Madman Dreams of Turing Machines. Well, Dr. Levin, let's now talk about the next generation of gravity wave detectors, even beyond LIGO. It'll, of course, take many years to perfect the next generation, but some people think they will be space-based. Things like LISA, the Laser Interferometry Space Antenna. The European Space Agency is also getting in the game, making their proposals. And what they want to do is listen in some sense, on creation itself. So what are your thoughts about listening in on the Big Bang?
Yeah, so LIGO's, the range of, if you like, gravitational wave sounds that it's sensitive to, overlays with the range of the piano. It literally happens to be in the human auditory range, although it's way too weak to pluck our eardrums. We couldn't hear it, but LISA would be detecting much lower notes. And we think that the Big Bang, when it happened, literally made a bang. It was this kind of cacophonous sound of ringing the drum of space-time, just in a noisy mess. But over the 13.8 billion years of its evolution and its expansion, those notes became lower and lower. And so now we would need a different instrument to detect such low notes. And LISA, one of the space-based instruments, aspires, among other things, maybe to pick up the remnant sound of the explosion of the creation of the universe. And it is, in fact, a space-based mission that will be many years off before it actually launches.
Now, I understand that when you turn on your TV set, especially an old one, you get that white noise, that snow on the TV screen. Mm-hmm. Some of that snow comes from Jupiter, the planet Jupiter, which is quite active, but some of it actually comes from the Big Bang itself. Radiation in the microwave range, which actually causes some of the snow you get on these old TV sets, which is incredible.
It has to be an old TV set with the bunny ear antennas, yeah.
Right.
Really old-fashioned.
Right. Not digital, but yeah, in some sense, you could pick up remnants of the Big Bang itself.
Yeah, some large percent, a few percent, I think, is actually the light left over from the Big Bang, because what confuses people is that the Big Bang didn't happen in one location in the universe. It happened everywhere. Everywhere we are was once the center of the explosion, that when the Big Bang happened, the entire space and time expanded, and we all live at what was once the center of the Big Bang.
Okay, now, we used to have this old picture of the Big Bang, that there was this explosion that set into motion eventually the galaxies and the stars and the planets. But there's a new wrinkle on all this called inflation. Last year we had Dr. Alan Guth of MIT on the airwaves talking about inflation, but explain a little bit about how inflation has changed the picture a bit concerning the Big Bang.
Well, it's proposed by Alan Guth and others that a very tiny patch of the universe very early on, maybe a trillionth of a trillionth of a trillionth of a second after the Big Bang, a very tiny patch of the universe caught itself in a kind of high-energy state, almost like it caught fire, in an analogy, and it expanded incredibly rapidly. The universe began to expand at an accelerated rate, and so much so that the entire observable universe that we live in right now would have fit inside that tiny region that inflated. And it's a very interesting theory for many reasons. One is it sort of explains why the light that you just described that we get from the primordial universe left over from the Big Bang is the same temperature in one direction as it is in the opposite direction coming from 92 billion light years away. So that seems completely impossible if it's not for a model like inflation, which says, well, that was all once in a very, very tiny, tiny part of space, and it just grew in an inflated way to become so big. Inflation also explains the sort of seeds of large-scale structures like galaxies and clusters of galaxies. So it's a very important model, but we don't have great details about what caused this inflated expansion. We don't have great details about the source of the energy. And so that continues to remain a kind of area of inquiry and also a mystery.
Yeah, and also it has philosophical consequences, right? Because if the Big Bang was a quantum event, if you wait long enough, quantum events sometimes repeat themselves. And so it means that in some sense, Big Bangs could be happening all the time, someplace far, far away. There could be more explosions taking place, which leaves us to a situation where we have parallel universes. This is almost science fiction, but isn't that where inflation is taking us?
Yeah, inflation has definitely foisted on us the necessity to consider the possibility of a multiverse, that our Big Bang wasn't the first and it certainly won't be the last, that there are other universes that have inflated, maybe some less successfully than ours, maybe some more successfully than ours, maybe some of those universes just collapse nearly instantly and don't house galaxies and people in them to look at the galaxies. And so that idea seems to be very much hand in hand with the idea of inflation. It becomes much harder to believe that this is the only universe.
Now, some people would say, bah, humbug, science is based on testable, reproducible, and falsifiable results. And how do you falsify parallel universes? Well, unfortunately, we have run out of time. And if you want to find more about this thing, go to Jana Levin's website, and her book is called Black Hole Blues and Other Songs from Outer Space. So, Dr. Levin, thank you so much for being on Science Fantastic.
Thank you so much for having me. Fun to talk.
You're listening to Science Fantastic.